Dear students, allow me to ask you a very silly question. If I take a coin, it has heads or tails, and I flip this coin, what is the probability that I get heads? Many of you will jump out and say 1/2. But what is that number that you jump out and scream? Let's try to understand. Suppose that I conduct an experiment and I am going to toss one coin 5 times. So here, to save time, I have 5 coins. So I toss them, and let's see what we had. So I had tail. First outcome was tails. So trial number 1, I got a tail. Trial number 2, I got heads. Trial number 3, I got tail. Trial number 4, I got tail again. And let's see what happened for trial number 5. It was heads. Let's see what is the average number of times we got heads on this experiment. So the number of heads divided by number of trials. In this case, we had 5 trials and only 2 heads. So we got some ratio of the form 2/5. Let's try throwing the coins again. So we throw the coins again. Let's see what we have now. Now we have first trial is heads. Second trial is tails. Third trial, heads. Fourth trial, heads again. And last trial was tails. So in this experiment, the number of heads divided by the total number was, on the denominator it is 5. So we have 1, 2, 3. This time we got 3/5. You can see that the results of first experiment do not agree with the result of the second experiment. If we were to combine those two procedures into one whole experiment, let's see what is the total number of heads we have over, in this case, n is 10. If it was an experiment consisting of 10 results and I performed one such experiment, I have 10 results, and then how many heads? 1, 2, 3, 4, 5. What do you know? 5 over 10 is 1/2. But is there a guarantee that if I were to perform 10 flips, I will again get the number 1/2? What is the significance of the number 1/2? Probability, guys, is extremely tricky because, let me tell you a little secret, I decided to teach this class. I was excited to teach this class because I myself have no idea what probability is. And let me try to explain it so you don't jump on me just a moment, right? Probability has certain axioms. We can state those axioms and using those axioms make a bunch of calculations. But the problem is the following. when I make a branch of mathematics axiomatic, I lose connection to the intuitive meaning. I might know precisely that my calculation is correct, but I have no idea what the calculation means. It loses all touch with reality when it's truly abstract. On the other hand, I might know precisely what my calculation means, but have zero idea about the correctness of that calculation. Maybe the calculation is right, maybe wrong, and I have no idea how wrong or how right it is. And that's a major problem. So, below this video, I will attach a link. There was a 1961, I believe, very great, amazing demonstration, and that's really a good introduction to probability. If you're watching my video, please make sure to watch the video that I will put as a link below. Now let's try to think, why would we jump up and say that probability equals to 1/2? What do you mean by that? What you mean, I think, is something rather metaphysical. You cannot tell when you flip a coin whether or not you get tail or heads. You cannot know if you flip the coin twice how many heads you will get. If you flip the coin 100 times, arguably you still do not know how many heads you will get. The sequence 1, 2, 3, 4, 5, the sequence is non-deterministic. I do not know what would be the outcome for 1, 2, 3, 4, 5, and onwards. This is a non-deterministic sequence. But I imagine that if I take the average number of successes divided by number of trials, so if I define H to be success and NH to be number of successes in n trials. If I define n like this, I might have the belief that the limit as n goes to infinity of nh divided by n will indeed be 1/2. So think about it. I have no idea what the sequence will be. A priori, before performing the experiment, I have no clue what would be 1, 2, 3, 4, 5, and onwards. And yet I claim, rather difficult thing to imagine, I claim that I will know the limit of the ratio of the sequence, right? So if I take the number of heads divided by the total number of trials, as the number of trials increase, deterministically now, the numbers will converge to 1/2. So I cannot tell 1, 2, 3, 4, 5. I might not be able to tell even up to 100 or 1,000 or 1,000,000, but this ratio will tend to the number 1/2. How can I make such a claim? Well, I have a sense, when I think of probability, of balance and justice. You think this coin, if it's true that the coin is fair, then that means that nature has no preference whether to select tails or heads. And how do you verify that nature has no preference? If you give nature enough opportunities, it will show you that it has no preference for heads or for tails. Give it enough opportunities and you will see that. But what's enough? To be truthful, I do not know if 100 is enough, or 1,000 is enough, or 1,000,000 is enough. How do you know what's enough? It's possible, at least it can happen, right? It might be something you not expect, but it could be that I flip a coin 1,000,000 times, and the coin is fair, and it just happened that the coin always landed on tails. It is possible, but you think that, well, those were quite many trials. You want to stop there. To know probability for sure is to be able to perform infinitely many trials. And not only perform infinitely many trials once, but to perform infinitely many trials repeatedly to verify that our experiment is correct. I have to perform infinitely many trials and get the number 1/2. Somebody else performs infinitely many trials and gets the number 1/2. I have to perform an infinity of experiments, with each experiment consisting of infinitely many trials. Clearly, that's not something that you would consider possible. So, you might have this limit equal to 1/2 metaphysically, because you presume or somehow know that nature has no preference. You expect it to be 1/2. Okay? Let me illustrate this point a bit more deeply with a deterministic sequence. With a deterministic sequence, like let's take the sequence 1 over n for simplicity. Here is the sequence 1 over n. It is a deterministic sequence. Why is it deterministic? Because a priori, I know what would be happening on the first trial. First trial, I get the number 1. On the second trial, I get the number 1/2. On the third trial, I get the number 1/3. On fourth trial, I know I will get the number 1/4. And so on, right? With a deterministic sequence, so for example, if I take the trial to be 10 to the power of 6, a millionth trial, that would be 1 over 10 to the 6, 1 over a million. A very small number. If 1 is a centimeter, 1 millionth of a centimeter is 1 micron. Very, very small. So with a deterministic sequence, I have this, this epsilon argument, and that would mean what? I can say that starting from the millionth row, I know my number is 0, and and the approximation is correct to within a millionth of a unit. Okay, so you can specify where you'll stop and where the numbers look like 0, right? So all the numbers from this row onwards look like 0 to within an error of at most 1 millionth. Okay? Now, with the non-deterministic sequence, there is the extra problem that I do not know where do I stop, where do I truncate? Is 5 enough? Or is 10 trials, as we had here, combined 5 and 5? Are 10 trials enough to see a number similar to 1/2? Or will I see a lot of oscillation? So sometimes I see 1/2 to within exactly 1/2, sometimes I see a huge error. How many trials is enough? Whereas the limit of a non-deterministic sequence might seem like something metaphysical, something very hazy and not reliable, it is nonetheless through this idea that I want you to try to imagine what probability is. We will say a few things about the axioms of probability, but they are only meant to capture that intuitive idea. Essentially, whenever you derive a new formula, whenever you want to have a sense of what is it that you are truly talking about, you want to consider the limit. Let me give you an example. So suppose you are claiming that boxer A is twice as good as boxer B in a fight. What is the probability that boxer A wins the match? Notice, we have two possibilities. Let's say we don't have a draw. It's impossible to have a draw. So then there are only two possibilities. Either boxer A wins or boxer A loses. Just because you have two possibilities, it does not mean those possibilities are symmetric. Many people make that mistake, as with the coin. You would say head or tail is equally likely. That's because the coin is fair. It has no preference to the possibility. But, for example, you either live past 200 years or you do not live past 200 years. Those are two possibilities, mutually exclusive, but they are not equally likely. Nature has a bias in preference of one possibility over another. Just like it has a bias in preference for boxer A. When you say boxer A is twice as good as boxer B, what you mean perhaps is that given enough opportunity, boxer A will show his superiority over boxer B. So what you imagine is infinitely many matches are being played, and we consider the number of times boxer A wins divided by total number of matches, and we take limit as n goes to infinity. What will happen if how do I understand the situation? This is limit as n goes to infinity, where the denominator is the number of times boxer A won the round plus the number of times boxer B won the round, and on the numerator I have the number of times that boxer A won the round. As the number of rounds go to infinity, we expect this number to converge. We expect nature to show its preference. Now, what would that preference be? Well, think about it. I can relate. If I had many trials, it was sufficient enough to observe that n of A is twice that of n of B, because if the boxer is twice as good, you expect the boxer to win twice as many times. So you expect the denominator to be twice the number of winnings of B plus the number of winnings of B. Why twice? Again, those are the number of rounds won by boxer A. You expect them to be double. So imagine if they played 1,000 rounds. So let's say they played 3,000 rounds. You imagine that 2,000 of those rounds were won by boxer A. So on the numerator, I also write 2, number of times we have B. Now, you can see that I can cancel out this number, and what am I left with? I am left with 2 divided by 3. Yes? 2 divided by 3. Now, I'm sure many of you know the band ABBA, and there is one song I actually like. The gods will roll the dice, their minds as cold as ice. Are your minds as cold as ice? If we roll a die that has 6 sides, what is the probability that number 6 comes up? Of course, you might expect, if the die is fair, you might already have an expectation. But what does this expectation mean? Here again, we have 2 possibilities. Either 6 comes up, or 6 doesn't come up. The die, if it's a fair die, has no preference which side to show up. It could be 1, 2, 3, 4, or 5, or 6. So what do we expect to happen here? We expect that to be limit as n goes to infinity of number of times we see 6 divided by total number of times, which is what? Which is the limit as n goes to infinity. I think of this as n of 6 divided by n of 1 plus n of 2 plus n of 3 and 4 and 5 and 6, yes? Now, if this is a fair die, with enough many trials, there is no preference. The number of times you saw 1 come up, or 2, or 3, or etc. are the same, correct? They are all the same number. So the denominator can be the same as 6 times n of 1, and the numerator I can write as n of 1 as well. Because if n is large, you expect 6 to have come up as many times as 1, 2, 3, or onwards. And therefore, you get your 1 over 6. Again, we assumed here, to solve this problem, we assumed that somehow we know that nature has no preference. And the other assumption is that given enough attempts, nature will show you what is it that it prefers. So if it has no preference, given enough attempts, it will produce as many 6s, as 1s, as 2s, as 3s, etc. And that's why we expect the number to be 1 out of 6. It's the limit of a non-deterministic sequence which we solve by our sense of balance and justice, a metaphysical sense.